Welcome to the second video of astronomy, the second one of earth science, and maybe the first one. I don't know, it depends on if you skipped the last one or not when you realize that we already did that stuff in class. I don't know what it's going to be. I don't know how you're going to use it. I don't know if these are going to be useful or not. I hope they are. I know that I'd like to do all this stuff in class, but we just can't all be in class together. So we have to still get through these notes one way or another, because as of right now, we still have a test at the end of the semester that we're going to have to get used to and we're going to have to get ready for. So we got to do the best we can. Anyway, let's pick up where we left off on the notes from last time. Our next note, now I know I'm not putting them up on the video here, but you can follow along, and maybe the best thing to do is just go ahead and write all of the notes down so that you can just reference them as I'm reading through. It's up to you, I guess, to see which one you like better. But anyway, here we go. Next set of notes. So we have gone all the way from the beginning of the universe. We have learned where we came from. We learned how we got here. We learned how the Earth is. We know how it moves. But we didn't always have the same ideas. So we have to go back in history, and some of you asked questions about why do we have to study history. Well, we have to study scientific history too to understand how we got to the thoughts that we have now. So let's go back. We're going to go back to the Middle Ages and a little bit before that, and we're going to talk about geocentrism. Now, geocentrism is the idea that geo means earth, centrism means center. It's earth center. It means the earth was in the center of the universe. And this is going to be introduced by a guy named Claudius Ptolemy. Now, you can see that in your notes, but what did he get right and what did he get wrong? Well, Ptolemy says that the earth is in the middle of the universe. He says that the planets go around earth, including the sun. And he says that everything that circles the earth moves in perfect circular orbits. So here's the thing. What did he get right? He got right that there's planets, and he got right that Earth is one of them. What did he get wrong? Literally everything else. So nothing he says is going to be right. The Earth is not in the center. We don't move in circles. The sun is not orbiting around the Earth, and pretty much everything is wrong. So let's move ahead in time. But it's okay, because remember, the theme of this class that you're going to find out is you're going to make mistakes, you're going to be wrong sometimes, but learning from your mistakes is the best way to learn. If you get everything right all the time, then you can't. That's not even an idea that we should entertain. You can't be right all the time. I'm not right all the time. We have to learn from our mistakes, and that's what makes us better. So we learn from them, science learns from them, and we move forward. So the next idea is heliocentrism. What's heliocentrism? Well, helio means sun. Centrism still means center. So this means that the sun is in the center. And now we're going to talk about the sun is just something that's in the middle, and all these planets go around the sun. We're getting better. That's closer to accurate. The sun is in the middle, and the planets do go around the sun. However, this guy, Nicholas Copernicus, he says that everything still moves in perfect circular orbits. No, they do not. We do not move in circular orbits. We're going to get to what we move in soon, but not circles. I'll put a big thing up right here. Not circles. Tycho Brahe. Now, he's the next guy. He's the next scientist that we're going to talk about. And he's going to live, kind of intermediate with Copernicus. And he makes, before we have telescopes, the most accurate observations to date. This is before Galileo invents the simple telescope. He can make them using a thing called a sextant. It takes 1/6 of a circle, that's where it gets the name from, and he calculates all this different geometry and this algebra and uses to figure things out of what's going on in the sky. However, all of this means that you can use really good data and still be wrong, because he thinks that Copernicus is wrong. He doesn't think that the sun is in the middle. Now, the next thing is super important, and it's something we're going to go over in class, and it's stellar parallax. Now, stellar parallax is what we use to determine that Tycho Brahe and all of our geocentric friends are wrong. The easiest way to think about this is to put your finger in front of your nose, and you can look past it. Now, if you close your eye, and I'm going to do it looking at the camera, I can see that my finger is in one place. But when I use my other eye, my finger has seemingly moved. Did my finger actually move? No, you watched it not move at all. That's basically what stellar parallax is. It means that when we on Earth are observing space, we can look at this far, far background of all these stars behind a certain point. It doesn't matter what the point is, we just look at the stars behind that certain point. And we can tell that when we're in one part of the year, say January, and then when we get to the exact opposite part of the year, say July, aphelion and perihelion may be coming back to you a little bit if you've studied, maybe not, who knows. 6 months apart, we have traveled halfway around the sun, which means when we look at that same point, which was my finger from earlier, in January as compared to July, it's not the same. The background is different. Stellar parallax is how we know the Earth is moving. Johannes Kepler then comes along and takes all of this information and comes up with 3 planetary rules. In fact, his planetary rules are so good that we still use a version of them today. Now, of course, we've updated and modified and thrown more math and physics and everything on top of it, but we still use these 3 basic examples today. So what are they? Well, the first one is the law of ellipses. What does that mean? It means that when we travel around the sun, we being any planet, we don't move in circles. We move in an ellipse. Now, as we're going to find out, Earth's orbit is pretty close to a circle, and it's about as close to a circle as you can get and not be a circle, but it's still technically an ellipse. The sun is at one of these focus points, and when we're back in class, you're going to do some work with me, and we're going to kind of go through the very basics of this math to figure out why exactly and how exactly we know that the law of ellipses is accurate. Now, the second law, the second of these 3 laws, is going to be the law of equal areas. And this one's a little hard to comprehend. It's probably the hardest one to comprehend, but don't worry. We're going to go over it in class, and I'm going to do my best to help you understand it. The law of equal areas says that if you move equal intervals of time, so let's use a month, let's call it actually 30 days. Let's not even call it a month because months can be different. Let's call it every 30 days, we are going to have the same area from that focal point, the sun, is going to be the exact same. So on the image on the PowerPoint, if you've looked at that, hopefully, or if not, go look at it. You can pause this and go pull it up right now. It's got purple and white alternating bands. Every letter, A to B, B to C, C to D, you get the idea, is an equal area. How does this work? Well, it's the way the math works out, and it's also what helps us understand that the law of ellipses is correct. It also kind of tells you about the orbital speed of the planets. The further away from the sun we get, the slower the planet goes. The closer to the sun we get, the faster it goes. Why? Well, closer to the sun, it has to take up more distance in the same amount of time. Remember, time isn't able to be changed, so we have to use those same 30 days. But we have to cover a much larger area than we do when we're way away and only have to cover this much area. The speed changes, the time does not. So, what is the third and final of Kepler's laws? Well, it's the law of harmonies. And basically, all this is going to say is that if you know how far away a planet is, then you know how long it takes to go around the sun. Or if you know how long it takes to go around the sun, you can kind of figure out how far away the planet is. Now, I know on your notes it says, what's the equation to this? Don't worry, I'm going to tell you the equation in class. You don't need to go look it up. I promise we'll talk about it. It's not that important. So what we can do next then is, you can see that I had a GIF of or GIF, however you, don't fight me on that, I don't care, of heliocentrism versus geocentrism, and you can see that one of them works and one of them doesn't. And if we had geocentrism and that was real, then we wouldn't need to worry about it because we would be dead, because we would have all run into each other at this point. So 3 more things for this video, 3 more important things, and 3 more things that you have to keep separate. The first of which is precession. Now, we're going to go over this in more detail in class, but I still want to give you a reference to this video that you can go back and watch. Precession is the change in the direction of an axis without the change in tilt. Meaning it's going to change the direction, but it's not going to change the tilt. The best way to see this is with a top. And I have a little clip of that on the PowerPoint, on the notes that I gave you. You can see that it's changing direction, but it's not changing its angle. For Earth, it takes about 26,000 years for this to happen, so it's not going to happen in any of our lifetimes or even any of our lifetimes combined. and it's also kind of affected by gravitational pulls. The next one is nutation. Now, nutation is the slight wobble of the change of an axis, and we say it's about ½ degree either other way. So that's why when I said the Earth's axis is about 23.5 degrees, it's because it's 23 to 24 to 23, kind of goes back and forth. And this one happens over a quicker time frame. It can affect some things like seasons, but it's not a big change. It's not why climate change or anything like that happens. The last one is barycenter, and simply put, barycenter is the center of mass between two objects. So if you're going to put something on a balance, just using my arms here, I don't know if you can see this part of my arm well because I'm wearing a dark pullover, but if you were going to put it, you had the same mass on this side and the same mass on this side, the barycenter is going to be the dead middle. Now, if we had a heavier object over here where my fist is, and we had a lighter object over here, we would have to move the barycenter. Think about if it needs to be closer to the massive object or closer to the lighter object and see which one it is. You can go look this up. You can go find videos. We're going to talk about it in class. But you need to know those three things. Precession is the change in the direction of the axis without the change in tilt. Nutation is the change in the wobble of the axis without anything else. And barycenter is the center of mass between two objects. Now, I know that these videos aren't super fun to watch quite yet. I'm sorry. I will make them more fun as we go along and have more time to edit them. But right now, I just need you to get this stuff down. I need you to keep doing your notes. I need you to keep doing excellent work. All of you in all three of my classes have been doing a fantastic job so far. I appreciate you. I know it's not ideal right now. I know it's not been the most fun. I promise I'm working on trying to make it a little more fun so we can work together a little more, but still be safe. Anyway, if you're watching this in the spring, if I use this again, forget everything I just said. All right, I will see you soon, hopefully soon, and I'll hope to keep seeing you in class. See ya.